Okay, hello. Please wait for a moment. Let me double check my setting. Yeah, I'm so sorry for the delay. So, yeah, okay, so let's start. So sorry for the delay. So, yeah, okay, so let's start. So sorry for the delay. Okay. Okay, so this week again, yeah, there aren't a lot of questions, so I have got something. I hope it is interesting prepared for you. Yeah, so this week, so let's take a look of the translating sentences problem. So I have an example here. So it says that Kai does not eat pizza unless it is Sunday. Okay, and then we want to use, let's say, P to represent the sentence Kai eats pizza. So P for pizza. And then S represents it is Sunday. So S for Sunday. So I want to make a translation so that this long sentence can be shortened by using this P and S as a symbol to represent it. So can we change it to the corresponding expression? So at this point, we don't know whether this is correct or wrong. What we want is we want to do a direct translation so that whenever this is true, then the translator expression will be true. And whenever this is false, the translator expression will be false. So we want to get a correct translation for this. Okay, so let's think about it. So I have two questions for you. So let's make sure we understand the setting. So first one is, suppose that it is not Sunday. So will I eat pizza? So first of all, it says that unless it is Sunday. So except that it is Sunday, then I will be following this rule. I will not eat pizza, right? So that means that the first one, it says that if it is not Sunday, then I should not be eating pizza. So this is yes. If this is true, then this will be yes. So suppose that this is true, then this is the meaning for the above sentence. Okay. Oh, cool. Yes, very good. So I see an answer. But the other one is, if it is Sunday, so does Kai eat pizza? Now, this is a tricky question. Okay. So here it just says that Kai does not eat pizza unless it is Sunday. It actually doesn't tell what happens when it is Sunday, right? So if it is Sunday, Kai may eat pizza, or Kai may eat other things, or Kai may eat nothing, right? So even if it is Sunday, we still do not know whether Kai will eat pizza or not. So here, this sentence does not have any relationship with the above sentence here. Okay, so one possible way to do the translation here is that, okay, so we will see this is the exact case. So what we see is that if it is not Sunday, if it is not Sunday, then it would imply that Kai will not eat pizza. So not Sunday will always means that not eat pizza. Is that okay? And then I have just seen another possible answer. So someone says we can write it as P implies S. So P implies S means that if Kai really eats pizza, then it must mean that it is Sunday. So P implies S. Now this is also correct. The reason is actually because, okay, from our understanding, or because it is logically equivalent to say not S implies not P and P implies S. So the two cases, not S implies not P, and the case P implies S, these two expressions, they are logically equivalent. So they are always having the same truth value. So we can write either of them. They will be okay. Now the next one. So let's see. This is an example in the lecture note. So it says that you cannot ride a roller coaster if you are under 4 feet tall unless you are over 16 years old. So it looks like that the rule says, so let's say this is a rule. So it says that if you are not enough tall, so you're too short, you should not ride a roller coaster. But on the other hand, if you are 16 years old, then you can take care of yourself, so we won't have any restriction about the height problem. So we want to make a translation for this. So let me use these to represent. So R represents we can ride a roller coaster. T about the tall, the height requirement. So let's say T means it is over 4 feet tall. Yeah, so under over, yeah. So over here means that at least 4 feet tall. Yeah. So Y here means that it is over 16 years old. So Y talks about the year problem. Okay. So how can we do the translation for this one? So suppose that this is some kind of a rule. Okay, so let's see. So I have seen someone says R implies T or Y. Someone says that, yeah, the current lecture notes I just prepared today, so that's why there was a delay. So perhaps I will send it to you after this meeting. Okay, so someone says R implies T or Y. Good. Okay, someone says that not T and not Y implies not R. Very good. Okay, so let's double check. Okay, so here, so first of all, I will call it a common sense. Okay, common sense says that not, so if you are not tall enough and then you are not old enough, right? So if these two cases happen together, then there is no reason that you can ride a roller coaster. So this is from what I'm saying, the common sense here. So not tall enough and at the same time you're not old enough, then you should not ride a roller coaster. Okay. Now, the previous example that we have here is, so previous example, we have the word unless. Is that okay? So unless it is Sunday, then I do the first part. Okay. So not the second part implies the first part, right? The first part is not P. So not the second part implies the first part. So this is actually the first part. So what we can do here is, okay, so in the previous example, so we have an unless here. So unless is the case that we are talking about exception. So if it is not the case like this, we should follow the rule. If it is the case here, we may not follow the rule, okay? So if it is not the case here, then we should have the first part. And what is the first part? So the first part is easy. So the first part is something if something. So it is if the first part and then the second part. So it is if the first part means not tall enough, implies not riding a roller coaster. Is that okay? So this format, yeah, excellent. So this format is by the previous example. Oh, I see another case by Cody, which may not be correct, but let's get back here. Okay, but here, the second part comes from the previous example. How do we interpret unless? And the first part is actually coming from the common sense. I also see a lot of answers in the discussion board that are also correct. So one says that instead of writing this one, we write, okay, so I hope, okay, so let me double check. So instead of writing this one, so someone says that we can try to have this one, R, and then what? Let me do this. R implies T or Y. Okay, someone says, gives this answer. Now, actually, this is also correct. The reason is that this is of the form something implies something. So let's call it P implies Q. So P implies Q is equivalent to not P implies not Q. So this whole thing, so let me write it down, double check. So this whole thing is equivalent to Give me some time. Okay, sorry for the mess here. Yeah, so meanwhile, let's take away the last sentence. Okay. So what I'm claiming here is, sorry, there is a mess here. So let's see if I can make things better. Okay, so let's focus on this one. So we have originally this sentence, and then this sentence is of the form of, this is the P part, and then this is the Q part. So P implies Q. So P implies Q is equivalent to not Q implies not P. So not Q is simply the R part. And how about not P? Not P is, we can use the De Morgan's law. So negation of something and something is the negation of the first part or the negation of the second part. So this is just by application of the De Morgan's law. So I saw someone answering in a form like this, then I will say this is also correct. But now we have these two. So this one is actually coming from the so-called common sense, and then this one is from the previous example. Indeed, they are both the same. They are both correct. So how do we show that? We are showing that these two sentences, these two expressions are logically equivalent. So we can do so by using a truth table to do so. But today, let us do another case. Okay. So this is the case that I want to say. P implies Q is the same as not P, or let me write it here. So let me use the symbol here. It's the same as not P or Q. Is that okay? So they are the same. So we are making use of this knowledge to help us to show that the red expression is the same as the purple expression. So first of all, this one implies this one. It is the negation of the first part or the second part. So what is the negation of the first part? So the negation of the first part is by De Morgan's law. This is going to be T or Y. Is that okay? So this is the negation of the first part. Okay, if I want to negate it, so I want change this upside down, not into not. Okay, so it is into the normal form and becomes or, and then not becomes the normal form, and then or the second part. Second part is not R, sorry. So I should write not R here. Yeah, it looks better. Okay. And how about this one? This one is that okay? So this one is not P or Q. Is that okay? So it is going to be not P or this Q part. Okay, so this is not P or Q. Now we see this, there is a pointer arrow here. So let's do another one, another simplification. So this is going to be equal to what? So let me copy it. The first part is Y. The second part is, this one is not this one, not this one, or the second part. Okay, so okay, are they the same? So this is a red one, right? T or Y or not R. The second one is Y or T or not R. But we will see that because of this or is associative and also commutative, we can actually, all of them are or. So we can take away this bracket. So we can actually take away this bracket. So they are the same, right? And now, because they are the same, and then they are commutative, so we can change this one, t or y or not r, into y or t or not r. So that's why we can see that these two expressions, they are both logically equivalent. So in that sense, yeah, we find that this is correct. Okay. Okay. Now the next one. Okay, so this one, let's do this as a practice at home. So here it says that, so how do we calculate leap year? So normal year we have 365 days, but then in a leap year we have 366 days. So why? So normally we will say that we will have a leap year every 4 years, but it is not exactly true. It is because the Earth rotates around the Sun using 365 points, something like 2422 days per year. So each year it is something like 365.2422. So after 400 years, you will have 97 extra days, roughly. So in order to make these 97 extra days evenly distributed, so we will have one leap year every 4 years. But then, if a year is divisible by 100, we need to be careful. Okay, so for those years that are divisible by 100, unless it is divisible by 400, then it will not be a leap year. So year 1700 is not a leap year, 1800 is not, 1900 is not, but year 2000, it is a leap year. Year 2100 is not, 2200 is not, 2300 is not, but then 2400 is a leap year. So by using this, then we will now have 97 extra days every 400 years. Okay. So here, so go home and try to get the definition for what is meant by leap year. So you can do this by defining. So like divisible by 4, divisible by 100, divisible by 400. So you have these 3 different cases, and then you can define how do you check whether X is a leap year or not using this simple expression. Okay, so go home and do the practice. Yeah, it is fun. Okay. Okay, now, so let us talk about how do we solve the logic puzzle that we have last week. Okay. So this one is we have a bunch of people, and then we have black and white text, and then we need to get the answer from the tallest one to the shortest one, and then yeah, someone get the answer already, or I forget. Yeah, I'm too old. Maybe I have already talked about the answer already. So for this one, the answer is the last one. Just try to use B or W to encode the information whether the number of black hats is odd or even, and then each of the next guy can use the information given and the answers of the previous people to deduce correctly what is the color of his hat or her hat. Okay. Okay, so this one, yeah. So I guess maybe I've already talked about the answer, but then yeah, you can double check. The next puzzle is this one. Now, this is another puzzle. So this time we have 2 guys, and then yeah, let's say they are boys. Yeah, one is Peter, the other is John. They can see each other, but then yeah, everyone has a hat, either black or white. So they can both be the same color or not. Okay. So each one, after looking at the other people's hat, then they will go into separate rooms and then need to guess the correct answer for his hat. We don't need both of them to guess correctly. We just need at least one. So is there a way? So one method here is very simple. Okay. So let's say this guy, the tall guy, let's say it is John, and the shorter guy, let's say this is Peter. Okay. John always gets the same color as he sees, and then Peter always gets the opposite color as he sees. Is that okay? So this one, John, will guess what he sees, and then Peter will guess the opposite of what he sees. Okay, now we can very easily argue that this solution guarantees at least or always there will be one correct answer. The reason is that if both hats have the same color, then this guy, John, the same. Okay, John will guess correctly. But on the other hand, if the 2 hats are different, then the shorter guy, this one, will be the one guessing correctly. Is that okay? So no matter what happens, if the heads are the same color, then the taller guy will guess correctly. And if the heads are of different color, the shorter guy will guess correctly. Is that okay? But then this solution may not be easy to extend. Yeah, because, so for instance, let's say we have now three people. And then each one of them will have R, red, yellow, or green as the head color. So again, they can see the others, but then they need to guess their own. Okay. So how do they do so? So previously we have, oh, they have the same color or they have opposite color, but then for three people, yeah, then this will suddenly become complicated. So what we want to do here is we want to find a better description of the previous scheme. So that it can be extended to the case where we have three people or we have even more people. So let's go back a little bit. Okay. So here, what we are going to do here is let's use an alternative way of describing the previous scheme. Okay. So imagine we use 0, the number 0, to represent white. And then we want to use the number 1 to represent black. Is that okay? So white is 0, black is 1. Is that okay? Now the first guy, the tall guy, actually will be guessing correctly when they are having the same color. So when we see the number are 0, 0, or when we see the number 1, 1. Is that okay? So no matter which case that we see, the sum of the two heads will be an even number. Either we get 0 plus 0, which is an even number, or 1 plus 1, which is an even number. Is that okay? So this guy will be correctly guessing when the sum of the two colors is even. And similarly, this guy is guessing opposite color. So this guy will be guessing correctly when this is a 1 and he is 0, or when this is a 0, he is 1. So he's guessing correctly when the sum of the head colors is an odd number. Is that okay? So this represents even, this represents odd. Now, with this as an example, then we can describe the solution, one possible solution for the scenario with three people easily. So let's say R represents the we use 0 to represent R, 1 to represent Y, and 2 to represent G. Is that okay? So this guy, so everyone will have the same encoding. So red always is 0, Y always is 1, G always is 2. Is that okay? So this guy simply guess the case that the total sum of the three heads is a multiple of 3. This guy will simply guess based on the fact that he will be guessing that the sum of the three heads is a multiple of 3 plus 1. And this guy will simply guess based on the belief that the sum of the three heads is a multiple of 3 plus 2. Okay? And then no matter what happens, one of these cases must be happening. Right? So the sum of the three heads is either a multiple of 3, or 1 plus a multiple of 3, or 2 plus a multiple of 3. Is that okay? So if it is 1 plus a multiple of 3, then the middle guy will be guessing correctly. Okay, so this is the solution for this case. So you can easily extend this solution when we have 7 people and then there are 7 colors. Is that okay? So yeah, so that's all for today. Yeah. So if you have any question, yeah, please come and ask. And then yeah, I will send, yeah, thanks. And then I will send this these slides. I will make some corrections of the slides and then send it out to you through the EE class later. Okay. Okay. So if you homework, thanks. So the homework I will. So we are going to upload the homework once we have finished a certain topic. So probably we will finish. Yeah, maybe next week, perhaps. So the assignment 1 will correspond to assignment 1 and all. So we have assignment 1 and assignment 2. So right, to E-class, yes. So they are corresponding to the first exam. Okay. There. Okay, just to make sure everyone understands correctly. So I have mentioned that the tentative days for the exams are on week 8, week 13, and week 18, right? Something like this. Okay. So how do we calculate the week? Okay, so we go by the NTHU calendar. So week 1 is actually starting from September the 13th. Okay. So today is the beginning of week 3. Okay, so we are having week 2 tutorial because last week we talked about week 2's material, so we have this as a week 2 tutorial. Okay, so today is the beginning of week 3. So I will make a reminder for you when the exam day is close by. Okay, so any other questions? Okay, if not, then yeah. So let's meet again on Wednesday. So Wednesday we will talk about an interesting IQ question called the what? The hardest logic puzzle ever. Okay, that's all. Thanks. Okay. Let me see. So I will stop streaming now. Thank you. Thank you very much.